Hello everyone, my name is Surender. I am from Tribuli. We are discussing about the tech talk. My subject is computer architecture. My topic is an overview of static pipelining. Abstract. A new generation of mobile applications requires reduced energy consumption without sacrificing a execution performance. In this paper, we pro- propose to respond those conflicting demands with an innovative statically pipelined processor supported by an optimizing compiler. The central idea of the approach is the control during each cycle for each proportion of the processor is explicitly is represented in each instruction. Thus, the pipelining is an effect statically determined by the compiler. The benefit hardware and that is it allows the compiler to perform optimization that are not possible on traditional architecture. The initial results indicate the static pipelining can significantly reduce power consumption without adversely affecting performance. Introduction. With the prevalence of embedded system, energy consumption has become an important design constraint. As this embedded system become more so stated, however, they also require a greater degree of performance. And of the most widely used techniques for the increasing processor performance is instruction pipelining, which allows for increasing clock frequency by reducing the amount of work that needed to perform for an instruction in each clock cycle. The way pipelining is traditionally implemented. However, the result is several areas of frequencies with respect to energy consumption, such as a necessary registers file access, checking for the forwarding and hazard when they cannot occur, latching unused values between pipelining registers, and respectively calculating invariant values such branch targeted addresses. Statically pipelined architecture. Introduction of pipelining is commonly used to improving processor performance. However, it also introduces some inefficiencies. First, in this need to latch all the control signals and data values between pipeline stages. Even when this information is not needed, pipelining also introduced branch and data hazards. hazards. Branch hazards result in either stall for every branch, the needed of branch redirectors and delays when branches are mispredicted. Data as a result in need for the forwarding logic, which leads to necessary register file accesses. Experiment with a simple scalar. Running the MI benchmark should indicate that 27.8%. The register reads the necessary become the values will be replaced from the forwarding. Additionally, 11% of registers write the note need to due to their only consumer getting the values from the forwarding instead because register files energy consumption has a significant production of processor energy. This is necessary access or bit wasteful. Data path of statically pipeline processor. Cycle operation. If the PC is used on a input in the ALU, then the result is placed in the track register. Otherwise, it is placed in the ALU register. In the CP1 and CP2, registers are used to hold the values copied from the one of the other internal register. These copy registers are used to hold loop invariant values and support simple register renaming. For instruction scheduling, since these internal registers are small and can be placed near the position of the processor that is accessed, they are accessible at the lower energy cost than the register files because more details of the data path are exposed at the architecture level. Changing the micro architecture are more likely to result to need for recompilation. However, this is less critical for the embedded system, where the software and a system often packaged within the hardware because registers are exposed on the architecture level. Because these registers are exposed at the architecture level, new level of compiler optimization can be exploited as will demonstrate session 3. Each statically pipelined instruction consists of a set of effects, each of which updates some proteins, pot, portions of the processor. The effect that are allowed in the each cycle mostly correspond to what the baseline 5-stage pipeline can do in one cycle, which includes one ALU or FPU operation, one memory operation, two register reads, one register write, and one sign extension. In addition, one copy can be made from the internal register to one of the two copy registers and the next sequential instruction. Address can optionally be saved in the SQ register. Lastly, the next PC can assign the value of the internal register. If the ALU operation is branch operation, then the next PC will only be set according to outcome of the branch. Otherwise, branch is unconditionally taken. Evaluation. This session will be presents the preliminary evaluation using benchmarks compiled with our compiler and then hand schedule. As described in the previous section, the benchmarks used are the simple vector addition. Example for, from the previous section and the convolution benchmarks from the response. Convolution was chosen because it is a real benchmark that has a short enough main loop to make scheduling by hand feasible. To extended then GNU assembler to assemble statically pipelined instruction and implemented as a simulator based on the simple scale as shown on the order to avoid having to compare the standard C library. We allow the statically pipelined code to call functions compiled for the MIPS in order to make for the fair comparison. We set a number of iterations to 1 lakh for the both benchmarks. When the compile for the static pipeline, over 98% of the instructions executed are statically pipelined. Once one with the remaining MIPS instruction coming from the call to print from the MSPI baseline to programs were compiled with the VPO MIPO ports within the full optimization enabled. Thank you everyone.